Hello and welcome to this video tutorial. Today we're going to be examining the Doppler effect. We're going to be looking at it in terms of calculating the apparent change in frequency that an observer would notice as either they or the source of the sound are moving toward or away from each other. Remember, as always, to pause or rewind the video as you need to. Let's begin. Now, the Doppler effect is essentially relating to the relative, it's the observed frequency that a person would notice due to relative changes of motion between the sound of the source and the observer. So, number one, when an automobile moves toward a listener, the sound of its horn seems relatively. Pause and try and answer number one. If an automobile is moving toward a listener, that means that person would hear a slightly higher pitch. Number two, when an automobile moves away from a listener, the horn seems, well, by contrast, this one would be noticed as a lower pitch. Now, what we're going to do for questions 3, 4, 5, and 6, we are going to quantify this observation, okay, with actual values. These are the equations we will use. Let's break them down. F prime is the perceived or observed frequency. It's the frequency noticed by an observer. In hertz. F is the actual frequency. It's the actual frequency of the sound source. Again, also in hertz. Then you have V, V sub O, and V sub S. Well, V is the speed of a sound wave. In meters per second. Now, the speed of a sound wave in air for this particular exercise is going to be a constant value, and we're going to use this value actually right here, 340 meters per second. That's going to be the value for the speed of a sound wave that we will use for this exercise. But please understand that the speed of a sound wave depends on the medium which it travels through and the temperature of that medium. So it depends on both of those things. We're just going to assume a constant 340 meters per second for this practice. V sub O, that's not V naught from the beginning of the school year. That's not initial velocity. No. V sub O is the speed of the observer. Now, if the observer is at rest, okay, then that means the speed of the observer would be 0, okay? If the speed of the observer is moving, obviously we're going to list their speed. V sub S is the speed of the source. Speed of the sound source. Okay, now we're going to use that, and what we're going to be doing is we're going to be calculating, if you look at the way the equations are set up, we're going to be, if the object and the observer are coming toward each other, then we are going to set up the following ratio. Speed of sound plus the speed of the observer divided by the speed of sound minus the speed of the source. That's only if we're coming toward, they're going toward each other. If they're going away from each other, then those signs are reversed. The ratio looks like the speed of sound minus the speed of the observer divided by the speed of sound plus the speed of the source. So just pay attention to whether or not the object is moving toward or away. Let's begin with number 3. A locomotive moving at 30 meters per second approaches a passing person standing beside a track. Its whistle is emitting a note of frequency 2 kilohertz. If the frequency of a sound is, if the speed of a sound in air is 340 meters per second, what is the frequency a person will hear? Part A, as the train approaches, and B, as the train recedes. Recedes means away. Approaches means toward. So we're looking for part A, the perceived frequency when they're coming toward each other, and the perceived frequency when they're going away from each other. Okay, we are given the speed of the locomotive, which is making the sound, so that would be the speed of the source. You are giving the frequency of the whistle, the speed of a sound wave, and you are told that the person is standing. That means the speed of the observer is 0. So let's list everything we're given. We're given the actual frequency of 2 kilohertz. Now remember, kilo means 1,000. So 2 kilohertz would be 2,000 hertz. We do have to change it from kilohertz to regular hertz. Okay, we're given the velocity of the source. That's the source is the locomotive, and that would be the 30 meters per second. We're given the velocity of the observer as 0 because the person is just standing, not moving, motionless. And we're given the speed of the sound wave at 340 meters per second. Okay, so we're going to record both of our equations. Pause the video so you can write down your equations. Okay, so then what we're going to do is we're going to be splitting our solution box in half. Top for part A, bottom for part B. Okay, part A, we want to find the perceived frequency as they approach each other, and then part B, we want to look at the perceived frequency as they get farther away. So let's go ahead and get our equations set up. Okay, and look at what we're plugging into. So for part A, we are going to plug in the actual frequency, which is 2,000 hertz, times V, the speed of sound, that's 340, plus VO, that's 0, over V, 340, minus VS. Okay, now at this point, what we have is we have 2,000 and on top, 340 plus 0 is 340. On bottom, 340, I'm sorry, I forgot to plug in what VS is. VS was the 30 meters per second. And on the bottom, we have 340 minus 330, which is 310. So a good way to start this with your calculator is begin by dividing those right there. Okay, 340 divided by 310. Okay, and then go ahead and multiply that by 2,000. Okay, doing so, you're going to get a value of a perceived frequency of about 2,194 hertz. So the actual frequency of the whistle, the train whistle, is 2,000 hertz. Okay, but if it's coming toward you, you're going to perceive something higher than that, and that's almost 200 hertz higher because it's coming closer. Part B, same idea, but we're going to be, again, switching the signs. So we have our 2,000 hertz times, okay, and for the first part, we're going to go 340 minus 0 on top, okay, and then we're going to go 340 plus 30 on the bottom. All right, so 340 minus 0, so we got 2,000. 340 minus 0 is 340 on top. On the bottom, we have 340 plus 330, which is 370. Now, again, begin by dividing the 340 over 370. Then multiply that by 2,000, and you should see that we are able to get about 1,838 hertz. And so what does that tell you? It tells you that because of this particular relative speed of 30 meters per second, we're hearing almost 200 hertz higher and almost 200 hertz lower than the actual frequency. Number 4, the siren of a police car at rest emits a frequency of 1,600 hertz. Okay, so we're given the actual frequency. What frequency will you hear if you are at rest? You're the observer. So the velocity of the observer is 0. But the police car is moving at 25 meters per second. So the velocity of the source is 25 meters per second. The velocity of sound we're still going to take at 340 meters per second, just like we did in question number 3. Okay, well, again, what frequency will you hear? We're looking for the perceived frequency, f prime. And that's going to be, again, part A is coming toward you. And then part B is coming away from you. Okay, we go get our formulas down. Go ahead and pause the video so you can get your formulas down and ready. Okay, now let's go ahead and divide our solution box in two. Part A, part B. Okay, going to fill in our work. I'm going to zoom in over here. We're going to have 1,600 hertz times our speed of sound is 340. Okay. I'm sorry. I should be working on the top part A. Sorry about that. So 1,600 hertz times our speed of sound, 340, plus 0, because the observer's at rest, over 340 minus the speed of the sound source, which is 25. So this would be 1,600 times 340 over 325 minus 340 minus 25 would be 315. Begin by dividing that part first. 340 over 315 times 1,600 is about 1,727 hertz. So we're noticing it's just a bit higher, a little over 100 hertz higher than our actual frequency of 1,600. Okay, same idea. We're going to go 340 minus 0 on the top as we're going away, and 340 plus 25 on the bottom. And that would mean we're going 340 over 340 plus 25 would be 365. 340 over 365, okay, is about 0.931 times 1,600. Oops, try that again. 340 over 365 times 1,600, okay, is about 1,490 hertz. So again, we're looking at a little bit more than 100 hertz greater as the police car approaches the observer, and a little over 100 hertz less than 1600 as the police car is going away from the observer. Question number 5. A train at rest emits a sound, a frequency of 1,000 hertz. So again, we're given the actual frequency of the train whistle. An observer traveling in a car from the sound with a speed of 30 meters per second. So in this case, it's slightly reversed. The speed of the observer is now given at 30, and the speed of the sound source is now 0 because the train who's making the sound is at rest. The speed of sound is still going to be 340, just like it has been. Okay, you're looking for the frequency heard, the observed frequency. Okay, as the train is going away. So as the car is going away from the sound, we're going to find out what it sounds like. Now, we should know that it should be less than 1,000 hertz, the actual frequency of the train whistle, but you're going away from the train, so you should notice something a little bit less, okay? How much less? Let's find out. Let's calculate that. Okay, now, which of these two formulas do we want? Well, specifically, we want the away version of the equation. And let's go ahead and we don't need to divide our box this time because we're only focused on the away portion of this. Okay, so plugging into that, the observed frequency is going to be 1,000 hertz times 340 minus 30, observer speed is 30, over 340 plus 0. The train source, the sound source is not moving. Okay, this is going to be 1,000 times, now 340 minus 330 would be 310 on top. And then 340 plus 0 would be 340 on bottom. So again, start by dividing those two. 310 over 340. Multiply that by 1,000, and the observed frequency would be about 912 hertz. Again, we said it was supposed to be less than 1,000, and it's almost 100 hertz less than 1,000 with that particular speed. Now, if you were going faster than that speed, then you would notice even less of a frequency, right? The faster you are going relative to the speed of sound, you're going to be noticing something different. All right, last one, number 6. We have a commuter train passing a passenger platform at a constant speed of 40 meters per second. A train horn is sounded with a characteristic frequency of 320 hertz. So we are given the actual frequency of the sound, and we are given the velocity of the source at 40 meters per second. Okay, a person on the platform is most likely just going to be standing there as the train passes by. So the velocity of the person, the observer, is going to be 0, and the velocity of sound wave is 340. So here's what we're looking for in this. Part A, what is the overall change in frequency detected by a person on the platform as the train moves from approaching to receding? Now, here's the hint. Find the perceived frequency as the train approaches, and then as the train recedes, and then find the difference between the two, okay? What does that mean? It means delta F, which is the change in frequency that a person would hear, is the observed frequency as it's coming toward you minus the observed frequency as it's going away from you. Okay, so we got to find each one of these individually and then subtract the two, and we'll get the change in frequency. Part B, we are looking for the wavelength. Okay, so the equations we're going to need, your standard Doppler effect equations. We're going to need them, but we're also going to need our wave speed equation, right? And we're solving for lambda, so you know you're going to have to divide by frequency in order to make that happen. Okay, let's go ahead and now I'm going to divide this up a little differently here. I'm going to go ahead and divide it up like this, roughly. Okay, and what I'm going to do is I'm going to find the frequency coming toward you, the observed frequency going away from you, and then we'll subtract the two. Okay, let's go ahead and zoom in. So we have a 320 hertz train whistle. So this is F prime, the observed frequency coming toward you. And it's 320 times 340 plus 0, the observer's at rest, over 340 minus, the train is going at 40 meters per second. Okay, so the observed frequency coming toward you, we have 320, and then it's times 340 over 300. So let's go 340 over 300 times the frequency of 320, and we are getting an observed frequency when it's coming toward you at about 363 hertz, roughly. Okay, that's not the answer yet, but it's going to help us get there. I'll put it down here. Okay, same thing. Let's find the frequency as it's coming, going away from you. So the observed frequency as it's going away from you, we're going to go 320. Okay, then I'm going to go 340 minus 0 this time, over 340 plus 40. That would be 320 times 340 over 340 plus 40 is 380. Again, go ahead and take care of the ratio first. 340 over 380 times the frequency of 320 is about 286 hertz. Okay, so that means the change in frequency would be my higher frequency, 363 hertz, minus my lower frequency, 286 hertz. .363 minus 286 is about 77 hertz, would be the difference that you notice. Okay. Part B, what is the wavelength detected by the person as the train approaches? So specifically, I want the frequency as the train approaches. Using our equation, V equals F lambda. Okay, solving for lambda, we have to divide by the frequency. And the wavelength is the wave speed divided by the frequency. So plugging in, we've got 340 meters per second over the frequency as it's coming toward you, 363 hertz. Okay, and we get a little less than 1, about 0.936 or about 0.94 meters. I hope you found this video tutorial to be helpful. Again, rewind to anything that you need to see again and pause as needed. See you next time.